What is electromagnetic induction? Take a wire loop, connect it to galvanometer, take a bar magnet, you will not see any deflection in the galvanometer. Move the magnet, you will see the deflection in the galvanometer, which means that there is current. Stop moving, again deflection goes away. In this particular drawing figure, you can do one more thing. First, bring it in and then take it out. When you bring it in, you find the needle deflecting in one direction. When you take it out, you find the needle deflecting in the opposite direction. It has to be a conducting loop. If you do not take a conducting loop, it won't work. There is no battery anywhere, but current can be produced. This current is called the induced current. If the loop is not complete, circuit is not complete, there cannot be any current, but some EMF must be there whether the circuit is complete or not. When the circuit is complete, then that EMF is responsible for induced current. When the circuit is not complete, that EMF is not going to create induced current. Many times it's better to talk about the induced EMF, because you do not need closed loop, closed circuit for that. So induced EMF, induced current. Some more changes can be made in this setup. You can make the setup in such a way that you can move the coil rather than the magnet. If you have such a setup, then you will find that when you move the coil, even though magnet is not moved, there is current, induced current. When the coil is not moved, there is no induced current. Another variation to this setup can be that you are able to change the shape of the coil. In this drawing, it looks like rectangular. So maybe by stretching the two opposite sides, you are able to change its shape. You don't move the magnet, you don't move the coil, but you just stretch these two sides away from each other, deforming the rectangle, and again you find that there is a deflection in the galvanometer needle. As long as you are deforming, there is deflection. So one point is about moving the magnet, other point is about moving the coil, and then about changing the shape. And then one more thing you can do, in some setup, you can rotate the coil without doing anything to the magnet. You just rotate, and again you find that when you rotate, there is deflection in the galvanometer needle. Initially we talked about bringing the magnet in. When you bring the magnet in, you are changing the magnetic field. So change in magnetic field, that gave rise to induced EMF, change in magnetic field. When you move the coil also, you are changing the magnetic field basically. So whether magnet is moved or coil is moved, in these two cases magnetic field is changed. When you were changing the shape of the coil, you are changing the area basically, area. Rectangle has some area, and when rectangle is deformed, that shape has some area which is different from the area enclosed by the rectangle. Area was changed, pulling the two sides that type of case. So area change gives rise to induced EMF, and then rotation, that is orientation change. Orientation change, which is like saying that area vector and magnetic field, angle between them is changed when you rotate the coil. So three things and change in them. It's not about how large magnetic field is. You can have extremely powerful magnetic field close to a metal coil, and there will be no current, no induced EMF. It's not about the strength, it's about the change. When you change any of the three things, or two things, or all the three things if you change, one at a time, two at a time, all the three at once, you find there is induced EMF. And if the circuit is closed, there is induced current. Right? That's induction. What is that single physical quantity that looks into all the three aspects that we have discussed? The answer is flux. Flux is that physical quantity which looks into all the three. Flux is B dot A, the same flux that you have seen in electric field discussion, Gauss's law. Flux is B dot A. So BA cos theta, magnetic field change, area change, theta change. All the three things are inside flux. Field change, area change, theta change. Now, what is the exact mathematical relationship? It is induced equal to minus d phi by dt. Induced equal to minus d phi by dt is the exact mathematical relationship. Minus sign shows that this induced EMF opposes the change in flux. It opposes the change in flux. flux has a unit of its own, Weber. And therefore, Tesla is also called Weber per meter square. Tesla is also called Weber per meter square. When there is current, then you can do little more math. You can write E induced equal to I induced times resistance, Ohm's law. And you can do even further math by writing I induced equal to dq by dt. So those problems that ask for charge, for them I equal to dq by dt you can put and you can proceed further. This experiment doesn't necessarily require a physical bar magnet. You can take another coil also. You know that a current carrying coil has magnetic effect. You will find the similar types of things happening. Whether it's a bar magnet or it's a current carrying solenoid or whatever, same thing. Now, how does one tell the direction of induced current? Or how does one tell the positive terminal of induced EMF? Positive terminal of induced EMF. Well, that minus sign you saw, induced EMF is such that it opposes the rate of change of flux. A great way to tell the direction is to make use of Lenz's law. Not that we cannot use E equal to minus d phi by dt thing, we can use that. Lenz's law is a great way also. Lenz's law says that induced current will be such that it will oppose the change. It will oppose the change. Change in what? Flux. Change in flux. So initially there was some flux. Somebody changed it by moving the magnet or by changing the area, whatever way, somebody changed it. That change will be opposed by this induced current. Now, one may ask, Lenzs law is fine for closed circuits where current is there. But what if there is no current, circuit is not closed? Well, you can just imagine that circuit is closed, and then you can figure out how should the current flow, and then by that you can imagine positive terminal will come where? Right? Now, consider this situation. There is a conducting loop. Left side we have a long wire. It has got current I. And this current is increasing somehow. It is increasing. So as the current increases, will there be any induced current in the right side loop? And if yes, what would be the sense? Clockwise sense, anti-clockwise sense? How will it flow? Left side current is increasing. Will there be induced current on the right side? If yes, what would be the direction? We can handle it in this manner. We will say that current is increasing. So magnetic field due to the left wire is changing. Magnetic field is mu naught by 4 pi 2 I by R. If current is changing, magnetic field is also changing. If one of the three things changes, then flux changes. So yes, there will be induced current. It's a closed loop. So there will be induced current. What will be the direction? Due to the direction will be such that it will oppose whatever caused change in flux. It will oppose that, whatever caused change in flux. Current increase caused change in flux. Current increase. Now, how to oppose that? Just see the effect it is producing. Effect is that flux is increasing. Current increase has the effect that flux is increasing. So it will oppose that flux increase. It will oppose that flux increase. Flux is increasing because magnetic field is increasing. Current is increasing, magnetic field is increasing, flux is increasing. So the current in the right side loop will oppose the increase in the flux. So it will oppose the increase in the magnetic field. It will oppose the increase in the magnetic field. Now due to the left wire, field inside the right side, is it into the screen or is it towards the viewer?
So inside the screen?
So into the screen?
Inside the screen. Yes. So to oppose that, you need field which is outside the screen. That's how you can oppose it. you will create a field which is outside the screen. Now, how will you create a field which is outside the screen? By clockwise or by anti-clockwise. That's it. Suppose it is anti-clockwise the way I have shown it. Suppose it is anti-clockwise the way I have shown it. Due to this anti-clockwise, another field will be created that should oppose that one. Will it oppose? Can you tell me what will be the direction of that field which is created due to this anti-clockwise sense current? Towards the viewer, into the screen. What's the answer?
So inside the screen.
Towards the viewer.
It is towards the viewer, I think. Yes, towards the viewer. It is towards the viewer. Look at a point inside, not outside. Due to this, you don't have to look at the field here. You have to look at the field inside. So see what's the direction of field here. You will find it to be towards the reader. Towards the reader. Due to this also, you will find towards the reader here. Due to this also, here towards the reader. Due to this also, here towards the reader. And due to this fellow here, same point, into the screen. So that anti-clockwise sense is creating a field which is opposing the original field. And original field was trying to increase. So opposition means opposite direction, which is perfect. So the answer will be exactly as shown, anti-clockwise. Anti-clockwise is the right answer. Any questions? Let me know. Now, let's consider another situation. Consider a wire frame. It's everywhere. Metal wires. Metal everywhere. This is also metal wire. And this metal wire can slide over these rails. Cross is the magnetic field everywhere into the screen. Cross is a field. Ignore these arrows. If this is moved to the right side, if this slider alone is moved to the right side, nothing is happening to these. Only the slider is moved to the right side. Let me put it this way. Will there be any current here at all? If yes, will it be anti-clockwise as shown here? Or will it be clockwise? Will there be no current? If there is current, will it be anti-clockwise as shown? Will it be clockwise? So, will it be induced? Will there be induced current?
Yes, sir.
Why?
Because as the slider moves, the flux enclosed in the area and keeps on increasing.
Flux increases due to what? Flux increases due to what? There are three things: magnetic field, area, and the orientation. Is it increasing due to magnetic field increase, the area increase, or the orientation change?
So the area?
Area increase, that's right. So as the slider goes to the right side, area increases. Magnetic field is everywhere same. Area increases, flux increases. So there will be, and it's a closed loop, so there will be induced current. Alright. Now, will the direction be as shown, or will it be opposite to as shown? For that, let's take a point inside the loop, this point. At that point, the current which is getting generated at that point should try to oppose the increase in flux. It should try to decrease the flux. At that point, field is cross. How can it decrease the flux? By making the field dot. By making the field dot. So due to this type of thing, will it be dot is the only question that you have to answer. Is it correct? Dot? Or not?
Yes, sir. Yes, sir.
Yes, sir.
It is correct. It is correct. So anti-clockwise is right, as shown. Any questions? Let me know. Next, a conducting circular loop is placed in a uniform magnetic field B equal to 0.020 Tesla with its plane perpendicular to the field. Plane perpendicular to the field. Okay. Somehow the radius of the loop starts shrinking at a constant rate of 1 millimeter every second. Radius starts shrinking. Find the induced EMF in the loop at an instant when the radius is 2 centimeters. If radius is shrinking, then area is dropping. Area is decreasing. Area is decreasing. That means flux is decreasing. The induced current will try to increase the flux. Let's say the instantaneous radius is r. So instantaneous flux is B times pi r square. So d phi by dt, phi is b into pi r square. So d phi by dt is ddt of b times pi r square. To differentiate, b is constant. R is variable. You will get twice r dr by dt. dr by dt is given. Find the induced EMF. Okay. So it's already done then. dr by dt is -1. dr by dt will be negative. Why negative? Because time increases, radius decreases. So dr by dt is negative. So dr by dt is -1 into 10 to the power -3 meter per second. Then R is 2 centimeters, so you can put it in meters, proper units. B is given. Well, I think everything is given. You can put the numbers and do the calculation. Put the numbers, do the calculation. See if you are getting the answer as 2.5 microvolt. 2.5 microvolt.
Yes, sir, getting it.
All right. Now note that you don't really have to worry too much about the negative sign here. That negative sign is just to say that flux change will be opposed, right? If you are interested in the number, then you don't have to bother about minus sign, just put the mod, vertical lines, right? And if at all you want direction, just use Lenzs law. If at all you want direction, use Lenzs law. So you can safely use E equal to d phi by dt with mod. And that minus will never trouble you. And if at all you are interested in direction, like this problem did not ask for direction, but if somebody asks for direction, then you can use Lenzs law. Any questions, or we proceed further? Let me ask you something. Suppose magnetic field is cross everywhere. If magnetic field is cross everywhere, will the current be clockwise or will it be anti-clockwise? Tell me.
So anti-clockwise?
Clockwise.
Let's see. Cross field and flux is dropping. So we must help the field so that the flux can be increased. We must help the field. So the current here should be generated in such a way so as to help this cross field. Okay, I should take inside point. So clockwise current at some internal point will be able to generate magnetic field into the screen, which will help this field to maintain the flux. So answer is clockwise. Any questions? Let me know. Some phi function is given depending on time. Induced is asked at t equal to 2 seconds. Very simple problem. Just differentiate. Find out minus d phi by dt. Differentiate and then put t equal to 2. See if you are getting 1.2 volt as the answer. And any questions, let me know. Look at this graph, D versus T. The area under consideration is given to be constant. So you can visualize some loop having this much area which is exposed to this type of field, time-dependent magnetic field. The question is, if the loop is placed perpendicular to the field, loop can be imagined on the plane of the screen, magnetic can be considered dot or cross, perpendicular to the plane. So magnetic field is perpendicular to the plane of the loop. Loop has the area given. Magnetic field is time dependent. So one question is, what is the average, E average, induced EMF average in each 10 millisecond, 0 to 10, 10 to 20, 20 to 30, 30 to 40. Every 10 millisecond interval from the beginning if you take, then what is the induced EMF average? Now average is different from instantaneous. We have discussed this. E induced equal to d phi by dt. This is at that very instant. But what is asked is E average. That will be final flux minus initial flux divided by the time elapsed, mod of that. In simple representation, it is delta phi by delta t. Right? Every 10 milliseconds we have to find this thing. So first 10 milliseconds, E average will be change in flux. Now because area is not changing, delta will be applied only to B, right? Area you can put from here. Delta B will depend which 10 millisecond are we talking about. If we're talking about first 10 millisecond, then delta B will be 0.01 minus 0. First 10 milliseconds, it will be area, this much. Final B 0.01 minus initial B 0 divided by 10 into 10 to the power minus 3. So 2 millivolt, isn't it? if I just talk about the mod. If I want to use the sign, then there will be minus sign. Two. First 10 milliseconds. Next 10 milliseconds, if you want, then area is the same. Then delta B, next 10 milliseconds, delta B is final B, 0.03, minus initial B here, which is 0.01, whole divided by 10 milliseconds, 10 into 10 to the power minus 3. Just simplify this, 0.02. It should be the double of this one. Okay, sign was important in this question because of this reason, that this is increasing function, this is a decreasing function. So sign reversal should take place. When we find delta B between these 2 points, it will be positive. When we find delta B between these 2 points, it is negative. So sign reversal will change place. That's important. Sign reversal will change place. Magnitude won't change. So 10 to 20 or 20 to 30, answer should be the same, but sign should reverse. So minus 4 millivolt should become plus 4 millivolt, 20 to 30. Then 30 to 40 and 0 to 10. They're all similar. Delta B has opposite sign. So minus 2 millivolt will become plus 2 millivolt, 30 to 40. That's it. Any questions in this part, let me know. Now, in which intervals is the EMF not constant? Not constant. In which intervals is the EMF not constant? Now this question is asking about EMF. EMF means instantaneous EMF, unless stated otherwise. Just like speed means instantaneous speed, unless stated otherwise. So in which intervals is the EMF not constant? So d phi by dt, area is same, dV by dt. The main thing is dV by dt. dV by dt is a slope of tangent. Slope is constant here, but then you got a curvature, again you got a curvature, then again constant. So 0 to 10, it is constant. Whether you talk of average EMF or instantaneous EMF, it is same here. Here also, whether you talk of instantaneous EMF or average EMF, it makes no difference. But here it matters. How you take the slope, it matters. Increasing function, decreasing function, and curvature, more importantly. Curvature is the key. So 10 to 20, how can the slope be constant? It's 20 to 30, how can the slope be constant? So in which intervals is the EMF not constant? Instantaneous EMF is not constant. In 10 to 20 and 20 to 30. 10 to 20 not constant. It will increase. It will increase. instantaneous EMF will increase in 10 to 20, and in 20 to 30 instantaneous EMF will decrease. Instantaneous EMF will decrease. It's not constant. So average is a different thing. We might have got 4 millivolt here in 10 to 20 and 4 millivolt here with plus minus signs difference, but that's average. Instantaneous will rise. Any questions? Let me know. This you have to answer. A metallic loop is placed in a non-uniform magnetic field which is not dependent on time. Will an EMF be induced in the loop? Explain.
Yes, sir, say induced EMF will be generated as the magnetic field is non-uniform and it will be keep on changing. Therefore, so the flux linkage will also change, which will lead to induced EMF.
Just a moment. Not dependent on time. Not dependent on time. So what is the meaning of keeps on changing? Think about it. Suppose I give you this situation. On the plane of the screen, this is a metallic loop. Field here is 5 Tesla. Let me say I make 4 quadrants. In this quadrant, field is 5 Tesla. In this quadrant, field is 6 Tesla. Here 7 Tesla. Here 8 Tesla. 4 quadrants, 4 fields, 5, 6, 7, 8. This is a metallic loop. Horizontal and vertical lines are no wires, they are my constructions. Will induced current be there? Or induced EMF? Okay, now let me ask you, on which 3 parameters does flux depend? On which?
The number of turns.
Yes, go ahead.
The number of turns of the coil, magnetic field, and the area.
Area, magnetic field. Number of turns, well, number of turns and area, they are related things. So you are missing the third point. Third. What is the third thing?
Orientation.
Correct. Now, we are not rotating it for sure. That leaves us with only 2 things, B and area. And it is no change in area. That leaves you with only one thing, B. Flux depends on B. Is flux changing? 5, 6, 7, 8. Is flux changing? Now tell me one more thing. Okay, no, why not?
So because in a particular area, so the flux is constant as magnetic field is constant in a particular area.
Area is this area. This is the area under consideration, area of the loop. And you are saying in one particular area, you are talking about 1/4 basically. You are saying in 1/4 of area, magnetic field is constant, so flux is not changing. When we say flux change can generate EMF, flux change with respect to what? With respect to what?
So with respect to time?
With respect to time. That's the key. With respect to time, not with respect to distance, that I go from here to there and 5 becomes 6, or I go from here to there and 6 becomes 8. No. Time dependence. It's a time dependence. At this very instant, whatever flux is through this whole thing, it is correct. It is sum of 4 fluxes, phi1 plus phi2 plus phi3 plus phi4. And none of those 2, 4, 5, none of them is changing. So overall phi also won't change with time. So it's not about non-uniform magnetic field. It is about magnetic field dependent on time. So non-uniform field can exist and nothing will happen. Nothing will happen. Any questions? Let me know. Everywhere it's time. Area as a function of time, phi as a function of time, d as a function of time. We stop at this point.